All right, so this lecture is going to deal with solving non-right triangles. Now, whenever we're solving non-right triangles, we need at least 3 pieces of information. So we'll either be given an angle, a side, and an angle, 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 side, 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 angle, side, 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 or side, angle, side. Now, when I say this, I'm referring to a triangle where you have these angles like A, B, C, and you have these sides opposite to each of those angles. And that's how we'd go about labeling it. So we need at least 2 angles and at least 1 side to be able to solve a triangle. Now, for these 3 cases above here, we use what's called the law of sines to solve them. The law of sines says that sine of A over A is equal to sine of B over B is equal to sine of C over C. So this is, these angles, sine of each of these angles divided by the side opposite of that angle. These ratios are always going to be the same. So law of cosines is what we'd use for solving these guys down here below. And this basically says c squared equals a squared plus b squared minus 2ab cosine c. So I'm making this video to highlight 2 different things that I didn't cover in class, which is how to solve using the law of cosines and how to solve this ambiguous case, the side-side angle case. So in all of the other cases, we're always going to have exactly 1 solution, but this guy could have either 0, 1, or 2 solutions, depending on what our information is. So let's go ahead and talk about that. So, in the ambiguous case of side-side angle, we are given 2 sides and an angle. So we're given, like for instance, this angle A. We're given a side B, and we're given another side A. Now I just drew a right triangle. We don't know that it's going to be a right triangle, but actually the right triangle is a special case of this. And this is where you get exactly 1 solution. So if we only have these 3 pieces and everything else can be modified as much as you want, so like you can make this length as long as you want it to be, or you can make this angle up here or this angle down here as wide or narrow as you want it to be, when we're stuck with just these things being fixed, the only time there's 1 solution is if this side, little a over here, intersects perfectly with this side over here, C, right? Which we weren't given what the length of C was. So this is going to be the case where sine of A is equal to A over B. Now, in a right triangle, we know that the sine of an angle is the ratio of the opposite divided by the hypotenuse. So sine of big A is equal to little a over little b. So this is, we could also do some algebra here, and we'd get b sine A equals A. So this is the case where we're going to have exactly 1 solution. So for instance, we'll be given 3 pieces of information. I'll use this kind of a format again later, where we're told what big A is, what little a is, and what little b is. We can plug those pieces into this equation, and if this side equals that side, then we know we have 1 solution and it's a right triangle. So there's another case, and that's going to be when little a is too short. So suppose we have a triangle that looks like this, we can always extend this length here of C, because C is variable, we haven't been told what it is. We can extend it as long as we want and end up dropping a perpendicular right here. So we can always make this perpendicular happen and call this guy H. Well, this guy H is going to have that property that the sine of A is equal to little h over b, or h over little b. So again, b sine of A is going to equal h. So in this case, little a, you'll notice little a is shorter than h, right? H is longer than A. So this guy is bigger than A. So this is going to be the case where, I'll write it the other way around, A is less than B sine of A. So in this case, we have no solution. So the reason for that is that you cannot make a triangle with A long enough because this angle is so narrow, or I should say actually it's not about the angle being narrow, but this angle doesn't allow for A to reach all the way down here. Our A given was too small, given B and angle A. Okay, so those are the two cases that are pretty easy to deal with. The other one is the tricky one, and that's where we end up having a possibility of two solutions. So suppose you have this same triangle going on, and here's B, here's angle A. This is again side-side angle. We get two solutions when this side A is so long that we could either drop him going that way or drop him going this way. Because we could extend C, this other side, to be as long as we want, we can end up making two possible triangles out of this situation. And this is going to happen. You always want to test this at the beginning before you get started with stuff. This is going to happen when little a is bigger than B sine of A. So this is the case where if you had dropped this same perpendicular, H, remember that H is equal to B sine of A. This guy is shorter than A, because if we had dropped A down here, he would reach all the way down here. Okay, so let's practice solving one of these now. So suppose we were given three pieces of information. And those pieces of information were that little a equaled 3, little b equaled 4, and angle A was 30 degrees. So this is a case where if you were to draw the triangle, you'd have, right, B over here, and you'd have A over here. You'd end up having this side-side angle case. So it's different from side angle side or something else where you'd have pieces on other parts. So it's only side-side angle that comes up like this. So first you want to find out, does it have any solutions? And the way we do that is we take B sine of A, which is going to be 4 times the sine of 30 degrees. And if you remember from your unit circle, or you just know your trig really well, you know that sine of 30 degrees is 1/2. So B sine of A is going to equal 2. And you compare that to 3, to A. So we know that A equals 3. So in this case, A, which is 3, right, is bigger than B sine of A, which is 2. So we know that we are going to have two solutions. So I'm writing really big. I might end up needing to use another sheet of paper, but I'll try this out. Okay, so Here we will have a triangle that looks kind of like this. This side B will come down there. And we'll also have a triangle that looks kind of like this. So this is A, this guy over here is B. Okay, so now we need to find all these other pieces. And this is a case where we want to use the law of sines. Now, why do we want the law of sines? Well, the law of sines has a piece that looks like this. Sine of big A over little a equals sine of big B over little b. We can isolate this piece, right? It's a string of 3 equations, the law of sines. And we want this because we have 4 unknowns in each of these pieces, in each of the law of sines or law of cosines pieces. You'll always have 4 unknowns. And we know 3 of these unknowns. We know big A, and little b. And here we have big A, little b. And so we can use this to solve for the final unknown, which is big B. All right, so sine of 30 degrees over 3 is equal to sine of B over 4. What we can do now is multiply both sides by 4, and that will isolate sine of B. And then the final thing we want to do is take inverse sine of both sides. So we can pull out our calculator now and find out what this is. So let's see here. We have inverse sine of 4 times the sine of 30 divided by 3. Oopsies, I messed it up. Got to make sure you close the parentheses there. Okay, so we get 41.81 degrees. Wonderful. So we now just have these 2 unknowns to solve for, big C and little c, which I happen to draw looking kind of the same. But this is supposed to be capital and this is supposed to be lowercase. Okay, so this is a point where the law of sines and law of cosines can't help us, but another piece of information can. And that is that the 3 angles inside of a triangle will always add up to 180 degrees. So we know that A plus B plus C is equal to 180 degrees. So C then is going to be equal to 180 degrees minus A minus B. So C is going to be, let's see, 180 minus 30 minus 41.81. So we have 108.19 degrees, all rounded to 2 decimal places. Okay, so we have one more piece to solve for, and that's little c. So how are we going to do that? We're going to use the law of sines again. So in this case, we'll use sine of big A over little a equals sine of big C over little c. So what I'm going to do is first do some algebra before I start plugging numbers in. Let's see. So I can multiply both sides by c, and I'll get c times the sine of a over a equals sine of c. And then what I want to do is still get c by itself. So I can multiply both sides by a over sine of a. And I'll have this set up. C equals sine of c times little a over sine of a. So c is going to be equal to the sine of 108.19 degrees. You might want to use the value stored in your calculator for that, just to hang on to as much accuracy as you can, times 3 over sine of 30. So let's find out what that is. So we have sine of, I'm going to put sign of answer so that it uses that same 108, this whole decimal, times 3 divided by sine of 30. And that gives me, whoops, what happened there? Oh, I forgot to put, I forgot to close my parentheses. So let's clear this one out. So we have sine of answer, close the parentheses, don't take the sign of the whole thing, times 3 divided by sine of 30. And we end up with 5.700. Let's just put 5.70. Okay, so are we done? Well, we solved one triangle. We didn't solve both of them. Remember, we said there are 2 solutions, so we're not actually done. Now the question is, which triangle did we solve? Well, we can find that out by paying attention to which angles are acute and which ones are obtuse in this case. So if I could label this more clearly here. Little b is going to be opposite of angle b, and so this angle down here is b. And then these guys are going to be big C and little c. So what I need to worry about now is, yeah, what I said earlier, whether or not they're acute or obtuse angles. So we see that C, angle C, is actually an obtuse angle, and B is an acute angle. So in that case, we're really looking at this guy down here as being the triangle that we just solved. So I'm going to call this triangle triangle number 1, and put little subscripts here, little 1 subscripts for each of our variables, just so we know that this is the answer for triangle number 1. We still want to solve triangle number 2. So how do we go about doing that? Well, let's look back at the big picture of what's happened here. Here's triangle number 1, just copied down. Triangle number 2 has this side A in here, so this is like A2 and this is A1. Well, if I fill in this information again, we really had that A was fixed, both big A and little a. And so this A2 is going to be the same length as A1, right? I'll go ahead and put subscripts on each of these. Little 2's down here. Okay, so A2 is the same thing as A1, which means that these guys are the same length. That also tells us that this is an isosceles triangle, this little guy in here. So these angles are going to be the same. That's a property of isosceles triangles. So if this guy is 41.81 degrees, this angle is also 41.81 degrees. And this guy over here, we can call this guy B1. I can call this angle right here B2. B2 plus this thing equivalent to B1 is going to be supplementary. They're supplementary, so it's going to be 180 degrees. So B1 plus B2 is 180 degrees. Therefore, we have 41.81 degrees plus B2 equals 180 degrees. So B2 is equal to, can I do this in my head? Let's not try. 180 minus 41.81 degrees. So 138.19 degrees. Awesome. Okay, so that gives us this cool piece of information for triangle 2. Now all we need to do is find C2, big C2, and little c2. Oh, and by the way, this is always going to work with these triangles that have 2 solutions. You'll always be forming an isosceles triangle here. This isn't a special case of that. That always happens. And I again made this guy really big, or not big enough, and this guy not small enough. Okay, so what do we do here? Well, we're kind of back where we were when we needed to find this angle. So let's go ahead and do that. To find angle little c2, it's going to be a tiny angle. We have a2 plus b2 plus c2 equals 180 degrees. So c2 is equal to 180 minus a2 minus b2. So c2 is equal to 180 minus 138.19 minus 30. We get 11.81 degrees. Are we done? Almost. Now we just have to find little c2. So we can use the law of sines again. We have sine of big A over little a equals sine of big C over little c. And we can solve for little c again. So again, we'll get c times sine of a over a equals sine of c. And so c equals sine of c times a over sine of a. So c is approximately equal to, let's see, I'll just start plugging all this stuff in. So we have sine of 11.81 degrees times a was 3, and then we're dividing by sine of 30. So we have 1.23. And now we've done it. We have solved this triangle, both of these triangles I should say, using the law of sines. Excellent. So we just have one more thing to do. I realize this is going kind of long. We're about 20 minutes in. The last thing we're going to do is do an example of solving with the law of cosines. So the law of cosines is used for solving triangles of the form, well, when you're given, law of cosines, I'm going to abbreviate it. This is used for solving triangles when you're given all three sides or side angle sides. So you're given the angle between two sides. The law of cosines says c squared equals a squared plus b squared minus 2ab cosine c. It sounds a lot like a squared plus b squared equals c squared, but then you have to subtract this chunk, because this works for every kind of triangle, not just right triangles. And in right triangles, well, big C is 90 degrees, so cosine of C is 0, and so you end up subtracting 0 in a right triangle. Okay, so let's take our little hypothetical triangle here. A, B, C, A, C, B. And let's just dive into it. Suppose we were given little b, little c, and big A. Let's say big A was 40 degrees. We don't know what little a is. Little b is 4. And little c is 3. All right, so what we want to do is figure out, well, what these other three pieces are. So we need an equation that has these three unknowns in it, and as the fourth unknown has one of these other pieces. Well, we're going to find it in the law of cosines, but it's not in this form that was written here. So it turns out the law of cosines, well, you know, each of these sides and angles is kind of interchangeable. You can just kind of rotate this triangle around. So this guy actually has three forms. We could also write it as b squared equals a squared plus c squared minus 2ac cosine b. And we could also write it as a squared equals b squared plus c squared minus 2bc cosine a. And this last guy is the one we're going to use, because it has a squared as our unknown there, but it uses b, c, and big A. So that's the one we want. So we have a squared is equal to 4 squared plus 3 squared, minus 2 times 4 times 3 times the cosine of 40 degrees. So A is equal to the square root of this whole business. So that's 25, 16 plus 9 is 25, minus 24 cosine of 40. You don't actually have to simplify this stuff. You can let your calculator do it for you. So A is approximately equal to, let's plug this guy in. So we have, where's the square root sign? Over here. Square root of 25 minus 24 times the cosine of 40 degrees. And you get 2.57. So we plug that in over here, and we got it. Okay, so at this point, one could finish solving this through using the law of cosines or the law of sines. But let me just give you a tip. Beware. The law of sines can't handle obtuse angles. So the law of sines can only give you outputs that are less than 90 degrees because of inverse sine and its range. That's something for a whole other lecture. So law of cosines is your best bet if you don't know whether or not there's an obtuse angle in your triangle. So let's finish this off using the law of cosines just to be safe. Let's try for this letter B here. So we could use this one over here, b squared equals a squared plus c squared minus 2ac cosine b. Let's try and solve for cosine b in that case. So b squared equals a squared plus c squared minus 2ac cosine b. So let's see, b squared minus a squared minus c squared equals negative 2ac cosine b. I could divide both sides by negative 2ac. b squared minus a squared minus c squared divided by negative 2ac equals cosine b. And then I could even go as far as to say b equals the inverse cosine of b squared minus a squared minus c squared over negative 2ac. And I'm running out of space, so I'm going to leave it at that and plug everything in. So this is kind of risky, putting all these things in your calculator at once, but I'll go for it. So we have inverse cosine of, so notice we have a whole bunch of stuff above this division symbol. You want to be careful with your parentheses. So I'm going to add an extra set of parentheses to make sure that I include everything above everything in this numerator together. So I have 4 squared minus 3 squared minus, minus a squared, So, well, it's okay. These are both being subtracted. So minus c squared and minus a squared. So I'm going to put, for a, I'm going to put answer, because it's a really exact version, or not as approximated version of the answer. Okay, divided by negative 2 times a, I'm going to again use answer for a, because that's what I have stored up there, times c, which is 3. So the angle is 91.43 degrees. Ooh, that's an angle bigger than 90 degrees. So it's a good thing we used law of cosines for that, because law of sines could not have handled it and would have given us like 88 point something or something like that. So yeah, it's a good thing we used law of cosines. Now what do we do for this last piece? Well, that same trick we always do, that these three add up to 180. So we can just do 180 minus what we got, minus 40, and that's 48.57 degrees. And there you have it. We're done. We just solved this triangle using the law of cosines.